In today's lesson, we are going to be looking at proportional reasoning. So before we get into that, or in class, we are going to do a kind of little math puzzle game to kind of just get our brains working. So it's a game called Skyscrapers. It's kind of like a 3D version of Sudoku. So you're going to be building different towers, and each towers are going to be sized 1 through 4. And we're going to use little linking cubes. Each row on our kind of neighborhood, our grid, has to have skyscrapers of different heights, 1 through 4, and you can't have duplicate sizes. So every height is going to have a 1, 2, 3, and 4. Every row is going to have 1, 2, 3, and 4. The same is going to be true for every column. So similar to how in Sudoku where every row has to have 1 through 9 and every column has to have 1 through 9, same idea with the shapes or the sizes of the towers. Now the rules, you're going to have numbers on the outside on the border in gray that are going to tell you how many skyscrapers you can see from that direction. The taller skyscrapers will block out your view of the shorter ones. So for example, this is an overhead shot of our city, so to speak. So if you look at each row and column, I did that backwards. You're going to look at each row and each column. You can see that in each one, there is a 1, 2, 3, and 4 sized building. There's no repeats in either, or there's no double ups. Here is a front view. So if I'm looking down looking at the grid, in this first row, I can see 3. I can see 1, 2, 3 buildings. Here I can see 1, 2. There would be 2 behind it. But I can't see it. Here I can only see 1, and here I can see 2. Right? I can see 1 and 2. So there would be maybe there's 2 in between them, or the 4, this tallest one is right behind it, or so on. But we can see only 2 buildings when we're looking at it. So that's the idea what we're referring to. I'll leave that up. 1, 2, 3, 1, 2, 1, 1. So that's kind of the idea of what I mean by what we can see. So again, you're going to need 4 towers of 1, 4 towers of 2, 4 towers of 3, and 4 towers of 4. So you can do this on your own at home if you want, but you're going to need little cubes. And this is an example of what the grid might look like. So a 4x4 grid. Here we can see this is telling us how many towers I'm going to be able to see in this direction. This tells me how many towers in this direction and so on. This tells me how many towers I can see in this direction. So you have to kind of rotate all the way around your grid. And then these ones over here tell us how many towers I can see looking in that direction from that side if I were to rotate it, and likewise from here and over. So again, we're going to do that in class, but just if you wanted an idea of what it looks like, you can use, if you have the cubes available at home, you can play this game there. So we're going to review a little bit of fractions and percents before we get into our proportions. So we want to look at how do we go from a fraction to a decimal. So in order to go from a fraction to a percent, we need to get to a decimal first. So if you're unsure about how to go from a fraction to a decimal, you are going to divide. So you're going to divide your fraction. So the top number divided by the bottom number. Right? We talked before about how a fraction is just kind of a different way to represent division. So if we have 3 divided by 4, that is going to equal 0.75. So that's my decimal now. Now if I want to go from a decimal to a percent, I'm going to multiply by 100. So that means 0.75 multiplied by 100 equals 75, which is 75%. If you wanted to kind of reverse this, if you wanted to go backwards, you could take the percent. If we kind of reverse our pattern, we would divide by 100. So 75 divided by 100 would give us 0.75. Now, going from a decimal to a fraction is a lot harder. It is easy to go from a percent to a fraction. If I wanted to go from a percent to a fraction, what I could do Again, I'll erase this just because it's going to be messy later on. But if I want to go from a fraction or from a percent to a fraction, I just always take my percent and put it as a fraction over 100. Because percent means per 100, right? So per 100. So 75%, 75 over 100. And then I can reduce it further if I need to. So let's try the second one, 13 over 25. 13 divided by 25 equals 0.52. And to go from a percent to or from a decimal to a percent, 0.52 times 100 equals 52%. And again, if I wanted to go backwards, divide by 100 or 52 over 100 and then reduce it as much as possible. So for the last column, we don't see anything in there. I want you to come up with a fraction of your own and figure out the decimal and the percent. Right? Try to not make it an improper fraction. We want to kind of keep our decimals and our percents within 100% or 1. So let's look at a quick example of working through this. So the equatorial radius, or basically the radius of the equator, of Venus is 78.5% greater than that of Mars. The equatorial radius of Earth is 5.3% greater than that of Venus. If Mars is 3,389.5 kilometers, what is Earth's equatorial radius? So a lot of information here, and it is a little bit wordy, so it might help you to highlight some information. We'll look at that later or further as we go through this course in terms of highlighting information. Right. So first of all, just main information, Venus is 78.5% greater than Mars. Earth is 53 or 5.3% greater than Venus. And then we know that Mars has an equator of 3,389.5 kilometers. So we know Mars, we then need to find Venus, and then from Venus we find Earth. So if Venus is 78.5% greater than Mars, I need to find out what 78.5% of Mars is. So in order to do that, if I want to find the percent of a number, I can take my number, and I can multiply it by the decimal version of the percent. So we talked about converting from a decimal or to a percent and backwards. So 78.5 divided by 100 is 0.785. So I'm working backwards. So that means that 78.5% of Mars' equator or radius gives us a value of 2,660, we'll say 0.76. Or round it to one decimal place, so 0.8. Now we need to add that to Mars's radius, because it's greater than. So the 3,389 plus 2,660.8 give us a value of 6,050.3. So this right here is Venus. Now I want to find Earth. Now I want to find Earth's radius. And Earth is 5.3% greater than Venus. So I can go through and do the same step, but there is a shortcut when I'm adding on or trying to find a new percentage or a new measurement based off a percent, right? So I can take Venus's measurement, which is 6,050.3, and I'm going to multiply it by not just the decimal percent of 5.3, but I'm also going to have a 1. So I'm going to multiply it by 1.053. And what this is going to do is this is going to save me from having to add to my original value. So it's going to save me one extra step. I'll explain why in a second. So when I multiply those two, I get 6,370.965. We can round that to 3,671 kilometers for Earth. So a nice trick is if we're trying to find greater than a value, or a percentage greater, or if we're trying to add a percent, we can do 1 plus the decimal version. Right? So the 1 represents the whole value, the initial value, and then by adding the decimal version, that means we're adding on the certain, whatever the percentage is. If we're trying to subtract a percentage, we would do 1 minus the decimal version, because it's going to be 100% minus whatever that certain percentage is, so you're going to only have a certain amount left over. So there is shortcuts if you wish, but it doesn't mean that you need to use that. Right? You can always go through step by step where we find the percentage, then add that to our original value, or find the percentage and subtract it from our original value. It works out the same. But there are shortcuts because it might be quicker. So moving on for percents, we're going to look at unit rates. So a unit rate is a comparison of different quantities of different units where the denominator is 1. This is a key thing here where the denominator is 1, right? So it's always per 1 of something. So if you want to write that down as well, per 1 of something, right? So some examples might be wages, right? What you get paid, right? Dollars per hour, dollars per 1 hour. Looking at typing speed, words per minute, speed, kilometers per hour. Right? So usually you see rates in terms of like units of time, right? But there's also many other things. So try to think of some other scenarios where you might find rates, or specifically unit rates. Quick example, we're going to look at two situations. We just want to explain what it's meant by the following rates. Right? So for example, a full 90-liter barrel starts leaking water at a rate of negative 0.75 liters per hour. So where's the rate and what does it mean? Well, it says right here a rate of negative 0.75 liters per hour. And what does that mean? What does that tell us? Well, it means that we lose 0.75 liters every hour. Right? So it's telling us how fast the water is coming out. B, the current exchange rates are US dollar equals Canadian, or $1 equals 1.26 Canadian dollars, and 1 Canadian dollar equals 0.79 American dollars. So we see our two rates. This one gives us two different rates. And what do they tell us? What do these rates mean? Well, there are the exchange rates. They're the exchange rates between money. So the US one means we'll say 1 USD, American dollar, is worth basically $1.26 Canadian. And vice versa, 1 Canadian dollar is worth 0.79 or 79 cents American. Right? So it's just showing the exchange rates between what $1 American is worth in Canadian and what $1 Canadian is worth in American. So these are also examples of unit rates because it's per 1 of something. So let's try to find the unit rates for some situations now. We're given unit rates and we interpreted them in the last one. So now let's try to find the unit rates for the following situations. First one is 140 steps in 25 seconds. So if we want to find unit rates, essentially all we're going to do is just divide or set up a fraction. So if we set up our first fraction, let's set it up as 140 steps divided by 25 steps. And that will tell us the amount of, not steps, sorry, 140 steps divided by 25 seconds, right? We've set up what we call a proportion or a ratio. Every 25 seconds, it's 140 steps, and we want to figure out what it is per 1 second. So in this case, we can divide 140 divided by 25, and we get roughly 5.6, and our units are going to be the first unit per the second unit. So steps per second. Now, what if you did it the other way? Would that give you something different? Well, let's try. So 25 seconds over 140 steps. If we divide that, 25 divided by 140, we get 0.18 roughly. Our units are going to be the top unit per the second unit. So it's going to be second per steps, or per step. Right? So it's just reversed. It's a different value, but which one's correct? Well, in this case, they're both correct. Right? They're both unit rates. They're just different scenarios or different kind of viewpoints or points of view. Right? The first one, the top one, is telling us how many steps are we taking per second. The bottom one is telling us how many seconds it takes us to do each step. So it's the same information, it's just from a different kind of viewpoint. So both are right. Obviously, there might be one that's a little bit more common than the other. So usually we see this one more than we see the other one, but that doesn't mean that they're incorrect. For number 2, 12 oranges for $6.99. So we have to think about, if we're going to set it up, we're going to create a fraction, what's going to go on the top and what's going to go on the bottom. Let me just go back and just put these here so we know where those are coming from. Well, do we want oranges per dollar? Or do we want dollars per orange? Again, either one would be correct if you set it up properly. It just depends on what you're more interested in, right? Or which one makes more sense to you. So we can go through and do both. So 12 oranges divided by $6.99. So 12 divided by $6.99 equals 1.72. We're going to keep 2 decimal places because of money. Oranges per dollar. So that means if I walked into the grocery store and I only had $1, I could buy 1.72 oranges. Now, thinking of it in that sense, that one doesn't really help us too much, right? That's not really reasonable. I'm not going to walk in, buy 1 orange and cut out 0.72 of another orange and walk up to the cashier. So let's look at it the other way. $6.99 divided by 12 oranges works out to 0.58. In this case, let me go back here. I forgot to put my numbers to tell us where these values came from. It was going to be dollars, which is our first one, or our top one, divided by orange. So dollars per orange. That one makes more sense. If I go in and I buy 2 oranges, I know it's going to be 58 cents for one and 58 cents for another. So that makes more sense. So in this scenario, I would probably use this one more often. Right? Not that the other ones are wrong. It's just a little bit more, it makes a little bit more sense in terms of real life situations. But both are considered unit rates because it's per one of something. Per 1 orange, per $1, per 1 second, per 1 step, all unit rates. The next example is going to use that idea of unit rates to help us figure out which is a better deal. So this is a good skill to have if you shop in bulk, like if you go to Costco or like Sam's Clubs or even any grocery store that sells items in bulk, Bulk Barn even, you're going to see a lot of unit rates there. Right, so at Sobeys, 24 cans of pop are on sale for $8.99, and a 1 liter bottle is on sale for or is sold for $1.69. Which is the better deal? And it might help us to know that one can has 355 milliliters and 1 liter has 1,000 milliliters. Now, different ways you can figure this out, but I would try to look at the unit rate for both situations. And the common value that we can get each to is probably going to be milliliters and dollars. So I want to look at each. I'm going to start with the bottle of pop because that is easily 1,000 milliliters. I already know that it's 1 liter bottle. So 1,000 milliliters divided by $1.69 equals $591.7. Let me just move this over a bit more. Actually, over here. And this is going to be milliliters per dollar. So that means for every $1, I can get 591 milliliters, or roughly 592 milliliters per dollar if I was buying the can or the bottle of pop. Now let's look at the cans. The cans are a bit different because we don't know the overall volume of pop that we're getting. We know there's 24 cans and we know one can has 350 milliliters. So let's use this to help us figure out how many total milliliters we have. So 24 cans times 355 milliliters equals 8,520 milliliters. Now I can set up a unit rate, same as the other one, divided by $8.99, and we can figure out which one is going to give me the better value. So 8,520 divided by 8.99 gives me 947.72, and it's going to be milliliters per dollar. Right, so again, those numbers in circles are just showing us where the units are coming from. So looking at these two scenarios, which one is the better value? Well, by looking at this one, I would say that let me just circle the image. The case of pop is a better value because we're getting more milliliters per dollar. Now, you might argue that it depends on the situation, which is very true, right? You do sometimes have to consider that, right? Maybe you're more concerned, or you just want a liter of pop. It's for a party, right? You're just going to bring a bottle of pop. Everyone has cups, things like that. Or maybe the 24 cans are more for home, or you're buying them for a store and reselling them. So again, there are situations where even though one is, from a dollar perspective, a better deal, you might still choose the other one. So that's okay, but mathematically we see which one is the better deal. So we've looked at unit rates, we've looked at some percentages, now we're going to look at proportions. So proportions are a statement of equality between equivalent ratios or fractions. Right, so the key thing here is a statement of equality. Equality just means equal, right? One thing is equal to another. And you can use proportions to solve for unknown values or quantities. And we can solve them using cross multiplication. So before we get into that, I just want to look at equivalent ratios, right? Because we're talking about setting up equivalent ratios, so let's just understand what an equivalent ratio is. Essentially, it's just a ratio that means the same thing. So here we have ratios, we have 3 to 7, we have 36 to 100. This could be written kind of similarly. Sometimes we can treat ratios similar to fractions, 3/7, depending on the situation. But if I wanted to create something equivalent, I'm going to basically either multiply or divide the values by the same number, similar to if I wanted to find an equivalent fraction. So for example, 3 to 7 might be the same as 6 to 14. Right? I just multiply both numbers by 2. Maybe I multiply them both by 4 and I get 12 to 28. I have to check that because I don't quite know my times tables off the top of my head. But again, right, those are all equivalent ratios to 3 to 7. Same thing for B, 36 to 100. I could multiply them both by 2 and get 72 to 200. I could also work backwards or reverse and divide. I could divide by 2 and get 18. I knew that one, not quite off the top of my head. 18 to 50, right? That would be equivalent. Right? So essentially that's what we're doing. We're trying to set up equivalent ratios or equivalent fractions in our proportions. And we're going to do that by finding or using cross multiplication. So here I have it set up as a ratio. Technically ratios are a little bit different from fractions, but in terms of solving them, we can treat them as fractions in this case. So I'm going to set up as a fraction. I'm going to cross multiply. So 1, I'm going to cross multiply. So I get 9 times 2 and 3 times x. So I get 18 equals 3x. I'm just showing that middle step just to show where we get these numbers and what we're actually multiplying. You don't need to show that if you don't want to. The second step is we're going to divide by the number with the unknown. So I'm essentially going to divide both sides by 3 to cancel out that x or that 3 there. So I get 6 equals x. Essentially, it's saying that 3 times something equals 18. So I do the opposite. I divide by 3 and I get 6 is x. So that means that 2 to 3 is the same as 6 to 9. Same idea for B, except it's already set up as a fraction, which is easy. Now I need to just cross multiply. 20 times 15 is 300 equals x times 12 or 12x. Now I'm going to divide both sides by the number with the unknown or by 12. And I get that 25 equals x. So that means that 20 over 25 is the same or equivalent to 12 over 15. So you might say, well, why do we need this? Why does it matter? Oops, we already did this one. We don't need that. Because it helps us sometimes in some kind of proportional situations, right? For recipes, for example. So a recipe for 4 people requires 300 grams of pasta. Now, how much pasta is needed if we had 26 people? Right? Maybe where we have a restaurant and we have a big party, we know kind of the basic recipe because no one normally cooks for 26 people, right? Maybe just 4 people like in a family, but we want to increase our meal. So what we're going to do is we're going to set up one fraction with the information that we know for sure, or one proportion, and we're going to compare it to another one with an unknown piece of information. So the first one, 4 people require 300 grams of pasta. Well, let's set up proportion. 300 grams for 4 people. And that's going to equal an unknown number of grams for 26 people. So now I have my proportion. So now I'm going to cross multiply 26 times 300 is 78, or 7,800, or 7,800 equals 4x. I'm going to divide both sides by 4, and I get 1,950 equals x. So therefore, we need 1,950 grams of pasta. Now, a couple questions you might be asking, well, how do I know which one to put where? Each side of the equal sign is going to be one kind of fraction or proportion, or one part of the situation. So usually we're given one piece of information, or one full kind of pair, you might say, right? 4 people, 300 grams. The other part, we don't know the grams, but we know the number of people. So there we kind of have our 2 parts. In terms of which one do we put on top and which one do we put on bottom, similar to when we looked at the unit rates, it doesn't matter. It doesn't matter which one we put on top and which one we put on the bottom, as long as we're consistent. Right? We see here grams and grams, people and people. They're on the same part of the fraction. So as long as that is kept consistent, then it doesn't matter in which spot we put them. Another example, a photographer finds that his 64 gigabyte memory card holds 2,132 photos. Let's say he wants to upgrade. Maybe he has a big wedding to go to, or he's traveling, so he's not, so they're not going to have a lot of. He doesn't want to bring a lot, or he only wants to pack one. He wants to know how many photos he can have. So again, we have some information. We have part of the information we're looking for, how many photos. We have size. So let's set up a proportion. Again, it doesn't matter which one goes on top or which one goes on the bottom, as long as we're consistent. So 64 gigabytes gives us 2,132 photos. So when we set up our proportion, it needs to be equivalent. So 256 gigabytes on top versus an unknown amount of photos on the bottom. Right, again, keep in mind, we've been consistent. Gigabytes on top, photos on the bottom. It's the same on both sides. Next, we're going to cross multiply. So 64 times x, 64x, and 2,132 times 256 was 545,792. Now we're going to divide by 64, the number with the unknown, and we get 8,528 for our unknown. Therefore, a 256 card will hold 8,528 photos. Lastly, we can use proportional relationships to kind of see or make predictions or compare players. So Cole Caulfield of the Montreal Canadiens scored 26 goals in 46 games last season before being injured, while Auston Matthews scored 40 goals in 74 games. If both players played a full 82-game season, who would have the most goals? So this one's a little different, because here we have 2 situations. We have Cole Caulfield, we have goals in 46 games. We also have Matthews with 40 goals in 74 games. So those are 2 full proportions, or 2 full fractions. We are going to compare each of those to a full 82 games. So we're going to do 2 different ones. So for Cole Caulfield, we have 26 goals in 46 games. And we want to see, okay, if he played 82 games, if he played a full season, how many goals would he have? Well, we have our proportion now. So let's cross multiply. 26 times 82, 2,132 equals 46x. We're going to divide both sides by 46, the number with the unknown. And we could expect him to have 46.35 is our unknown. So Cole Caulfield would be expected to get 46.35 goals if he played 82 games. For Auston Matthews, he had 40 goals over... Actually, let me do this up reverse. He had 74 games over 40 goals. Or it took him 74 games to score 40 goals, however you want to consider it. And we want to say if he played 82 games, how many goals would he get? Similar idea. Cross multiply. 40 times 82. 3,280 equals 74x. I'm going to divide both sides by 74, the number with the unknown. And we get 44.32 equals x. So that means if both players, or therefore if both players played an 82-game season, Cole would have more goals. We would kind of predict that he would have roughly 2 more goals than Auston Matthews if they both played a full 82-game season. So this is just an example of how we can use proportions in different scenarios to look for different things, whether it's to like increase a size or to kind of make predictions or kind of see what could happen, things like that. And essentially it's just an extension of looking at equivalent fractions, because all that's saying is that we're finding an unknown to make the fractions equivalent.